Right. Our next talk is by Yongwei on From Traces to Incorrectness. So whenever you're ready and mic'd up, please take it away.
You have to guess which one you are here.
Ah.
No, it's a different color.
Oh, yeah. Sorry, it's so small. I should have made it bigger. Well, anyway, my name is Yongwei, and today I want to present From Traces to Incorrectness, a type-theoretic approach. This is still ongoing, and actually we will talk about some past work and then pave our way to the current work. By the way, this is joint work with my colleagues from Purdue University, Zhou, Belyakova, Benjamin Delaware, and Suresh Jagannathan. So, right, we've already seen a lot of incorrectness logic. We know that incorrectness logic typically concerns reasoning of imperative programs. But when we shift our focus to functional programs, it poses the question that, well, what does an incorrectness type look like? To answer this question, well, the straightforward way will be try to incorporate the incorrectness triple like a type, right? And then the middle bit in the triple is a refinement type that captures the reachable values of the expressions. But the problem is that, well, types is good because it brings a lot of compositionality in the reasoning. But when we look at these two triples derived from these two subterms, E1 and E2 in the program, the question is, how can we compose them? So to answer this question, let's first look at, well, this is look at a abstract program where the green dots represent program states and the blue circles captures an incorrectness triple, which underapproximate the program behavior. Imagine that the program state here are captured by traces, like, okay, as in sequences of past events the program has already produced. And then the transitions here, we can think of them as transducer over those traces, because when we transducers are essentially a function that takes trace and returns trace. And because of that, we can think of transducers as a state transformer, where the state are represented by traces. I will elaborate what those traces are and how they can represent the program. But the high-level idea is that we want to incorporate this transducer idea as part of the type system to reason about the incorrectness. But before then, I need to talk about some background, which is first, type usually represent over-approximate behavior of the programs, right? So we first need to talk about, okay, what does under-approximate type means? We will first talk about this work, coverage type, and then I promise that I need to discuss what those traces represent and how they can capture the program effects. This will be the work for automata type. And at the end, we will see how we can combine them and also the transducer, which hopefully the resulting type system will allow us to do incorrectness reasoning for functional and effectful programs. Right. First, coverage type. So why coverage type, or what is coverage type? Here is a little natural number generator. What it does is simply it first generates integer x, and then if the x is non-negative, we just return x. Otherwise, we return 1. So and here and on the right-hand side, we have two types. One is the standard refinement type. The other is a coverage type. It's obvious that if you're familiar with refinement type, it's obvious that the natural number generator here always can be assigned this refinement type because it always generates the value it generates is always non-negative. But on the other hand, this coverage type cannot be assigned to this program because what, right? This is what I want to answer shortly. to answer that, like we need to understand what are refinement, what are coverage type, especially in contrast to refinement type. So look, notice that they have similar structure. They both have a self-reference to the value v. They both have a base type, and also they both have a qualifier that talk about that qualify the value v. But their semantics or their meaning are very different. Refinement type typically talks about the safety of the program. It says, well, for all value v that the program can reduce to, it should satisfy the phi. So the qualifier captures the safety of the program. On the other hand, coverage type concerns the completeness of the program, in the sense that, notice that we swapped the conclusion and the condition in the formula such that it essentially says, well, if a value satisfy our qualifier v, as in here it says, if for all non-negative values, the expression should be able to produce it. Well, this is, and then with this completeness mental model in mind, we can go back to our program. This natural generator is a natural number generator is not complete with respect to the coverage type specification because it cannot produce 0. The fix is simple. We just replace the 0. We replace the second branch 1 with 0, and then the natural number generator can indeed produce all the natural numbers, and the coverage type check succeed. So, so this coverage type, why would we need to talk about this coverage type? It is a form of underapproximate reasoning that concerns purely functional programs. But like the incorrectness often concerns effects, and let's talk about how can we use program traces to capture those effects. Here is a simple functional client that talks with effectful libraries. And the effectful libraries is here. The effectful library is an integer cell, has 2 API calls, read and write. How can we reason about this program? Well, we can augment the small step operational semantics that works on pure programs. We augment the operational semantics with traces, where we first have where the reduction of the term e begins with a context trace that captures what has happened before. It also, and then the second part, and then we also keep track of what are the new event produced as we reduce e to e prime. To ground the discussion, let's look at what those traces are. Let's say we evaluate our little program starting from a trace where there was a write 3. So, and then we know that the read will return 3, and this reading event will be tracked as we evaluate the program to write 3 plus 1. To further evaluate this program, we append the new event read returns 3 to the existing trace, and then the write 3 plus 1 will produce an event write 4. So with this kind of with this operational semantics that operate over traces, we can use it to captures Hoare-style reasoning where we have precondition and postcondition. Let's say for all the traces in the precondition, if we evaluate our term e under this trace and produce beta, then the context trace alpha concatenated with the effect trace beta it should satisfy our post condition. So really, the precondition and the postcondition are represented by a set of traces, which more concretely we can use regular expressions to represent them. And this whole automata type essentially says, well, if we evaluate this program, given that a non-negative integer was written, then the program, after the program evaluation, we ensure that the last event is also a write with non-negative integer. So I promised that we need to talk about incorrectness, but a more straightforward way will be just talk about how we can refute this whole automata type. And the refutation of whole automata type can be written like this, which is trying to find a precondition trace alpha and find an execution that produce some effect beta such that alpha calculated with beta is not satisfied by the post condition B. Like we are not diving into this in this talk, but we have tried to use symbolic execution and the derivative of regular expressions to guide the falsification problem here. Please feel free to you're recommended to go to tomorrow's talk at 11. But here what we are really interested in is how we can then plug in this transducer along with those underapproximate reasoning idea. As we said at the very beginning, transducer will allow us to allow compositional reasoning of the program. Well, what are the transducers? For example, the behavior of read here can be captured by a transducer that takes the input trace write x and it simply directly returns this output trace. On the other hand, the write operation here its behavior can be captured by another transducer that takes in write x as the input trace and returns write x plus 1 as the output trace. And so the transducer here we're talking about are really symbolic finite transducers, and which means that because there are many other possible pairs of traces that captures the behavior of read and write. And by leveraging the published result on symbolic finite transducer, we can easily compose these two transducer, which essentially compose the behavior of the subterms. What the composition does is essentially taking the output trace of the first transducer and match it with the input trace from the second transducer. With that, let's plug the transducer to a type. Here we have an underapproximate type from before, from coverage type, and it's attached with a transducer T. So here, the denotation of this type essentially says, well, for all input-output pairs of traces in the transducer, the program is able to witness them. And interestingly, this transducer, the denotation of this transducer is analogous to what the incorrectness logic does if we consider a weaker version of the formula. So the range or the codomain of the transducer essentially represents the reachable post state of our program, while the domain of our transducer, the input traces acceptable input traces to this transducer captures the presumption of our program. And then this formula essentially says, well, for all reachable post state, there exists some pre-trace that will allow you to find an execution of the program that lead to the post state. With that, I want to quickly summarize here that the transducing type is for incorrectness reasoning, a functional program that interacts with effectful libraries. We use underapproximate refinement type to capture the reachable values, and we use the transducer as a form of forward state transformer. Yeah, with that, I'm happy to take any questions.
So I was wondering, how do you compute the transducer for like read or write? Because that do user need to annotate those, or?
Yeah, for now our idea is that we ask user to provide them.
Essentially, I had the same question because in the refinement type, the phi must be finite.
Phi
in the refinement, you see you have finitely many phi. And I was wondering, what are you doing if you have infinitely many, but you also assume you have finitely many phi here?
Phi is qualifier.
Yeah, this is a property. So in terms of abstract domain, you have finite abstract domain.
Yeah. Here we mostly consider like discharge those qualifiers to SMT solver. So we haven't really looked at abstract domain and things like that. Yeah.
You have, but they are implicit.
Implicitly.
Let's thank the speaker again.
Oh.
The mic.